Desalination and microfluidics might sound like two very different worlds, but when combined, they open up a realm of innovative water purification techniques that are as fascinating as they are practical. Imagine harnessing the precision of microscale fluid control to separate salt from water. It's like orchestrating a tiny, high-stakes dance where every droplet is carefully guided to its destination. This is the promise of using microfluidic technology in desalination, enhancing the efficiency of salt removal while reducing energy consumption. One of the most surprising aspects is how microfluidic channels, often no wider than a human hair, can be designed to mimic natural filtration processes. By creating highly controlled environments, engineers can steer water and dissolved ions through specialized membranes or ion-selective layers that effectively separate salt from water. This controlled flow at the microscale not only accelerates the desalination process, but also minimizes waste and reduces the energy footprint compared to conventional methods like reverse osmosis. Isn't it remarkable that manipulating fluids on such a small scale can have a massive impact on addressing one of our planet's biggest challenges? Consider the potential of integrating microfluidics with advanced materials. Researchers are exploring the use of nanoporous membranes that, when combined with microfluidic channels, can selectively filter out salt ions while letting water molecules pass through. This not only improves the purity of the output water, but also offers a level of control that allows for the fine-tuning of purification processes. Could this be the breakthrough we need to make desalination more accessible and environmentally friendly in regions suffering from water scarcity? Moreover, microfluidic approaches offer unique advantages in modularity and scalability. Small chip-based systems can be combined into larger networks, creating adaptable desalination units that could be deployed in remote areas or integrated into existing water infrastructure. These systems can be monitored and controlled with precision, ensuring optimal performance even as water quality fluctuates. Imagine a future where entire communities rely on smart microfluidic desalination devices that adjust in real time to changing environmental conditions, delivering fresh water on demand. The intersection of desalination and microfluidics represents a thrilling convergence of engineering, material science, and environmental technology. It challenges us to rethink traditional water purification methods and explore how tiny channels and precise fluid control can be harnessed to solve global problems. As this field continues to evolve, one might ask, could microfluidic desalination become a cornerstone technology in our fight against water scarcity? With ongoing innovations and research, the answer seems increasingly promising, hinting at a future where clean, sustainable water is available to all. Desalination is the process of removing salt and other impurities from water to produce fresh water. And microfluidics, which involves the precise manipulation of fluids at the microscale using channels and chambers, has recently been explored to enhance traditional desalination methods. This innovative approach creates a controlled environment where chemical and physical processes can be optimized, integrating multiple purification steps into one compact device to reduce the scale of operations while increasing salt removal efficiency. For example, engineers have developed a microfluidic desalination chip that uses precise fluid channels to separate salt ions from water, significantly reducing the energy needed for the process. Imagine a tiny, high-tech sieve that not only filters out unwanted particles from a liquid, but does so with the precision of a watchmaker, ensuring only pure water passes through. Microfluidic principles in desalination rely on the laminar flow of fluids, which ensures smooth and predictable behavior in microscale channels, minimizing turbulence and allowing for precise control over mixing and separation processes. These conditions facilitate rapid diffusion and efficient mass transfer, crucial for quickly separating salt ions from water molecules, even in high salinity conditions. For instance, a research team designed a microfluidic device that uses laminar flow to create a stable interface between salt water and a freshwater stream, enabling efficient ion exchange and salt removal. It is like a carefully choreographed dance where every participant moves in perfect harmony, ensuring that each step is precise and coordinated to achieve the desired separation. The design and fabrication of microfluidic desalination devices involve advanced techniques such as soft lithography and 3D printing to create intricate networks of microchannels that facilitate controlled fluid movement. Materials are chosen for chemical resistance and durability under saline conditions, and the channels are engineered to maximize contact between water and selective membranes or reagents, optimizing flow rates and enhancing separation processes. For example, researchers have fabricated a microfluidic desalination chip using soft lithography, which includes a network of microchannels lined with ion-selective membranes that efficiently remove salt from water. Think of it as designing a miniature, highly efficient highway system for water molecules where each lane is engineered to direct traffic away from the main road, pure water. Microscale fluid control is key to enhancing salt removal in these systems as it allows for precise manipulation of flow rates and pressure to optimize ion migration and diffusion processes. By adjusting these parameters, engineers can maximize the efficiency of ion exchange and continuously remove salt from the flow without requiring high pressures or temperatures, thereby reducing energy consumption. For instance, a desalination system using a microfluidic setup finely controls the flow of seawater through ion exchange channels, achieving a higher rate of salt removal with lower energy input. Imagine a chef using precise control over the heat and stirring speed in a small pot to perfectly extract flavors, ensuring that every ingredient is optimally processed without wasting energy. Integration of membrane technologies with microfluidics further enhances desalination by precisely positioning ion-selective membranes within microchannels to improve water-salt interactions. This combination not only increases contact efficiency and reduces fouling, but also allows for the use of advanced materials that can selectively filter ions with high accuracy, leading to faster and more reliable water purification. For example, engineers have incorporated ion-selective membranes into a microfluidic device, achieving efficient separation of salt from water with minimal fouling and extended membrane lifespan. It is like integrating a high-performance filter into a sophisticated water pipe system, where the filter is perfectly positioned to catch every impurity without slowing down the flow of water. Energy efficiency and process optimization are critical in desalination, and microfluidic platforms offer significant advantages by lowering the energy required to drive fluid movement and perform separation processes. Optimized flow control minimizes wasteful energy expenditure by maintaining ideal operating conditions, resulting in lower operational costs and a reduced environmental footprint without compromising water quality. For example, a pilot desalination plant using microfluidic technology has demonstrated a significant reduction in energy consumption compared to traditional reverse osmosis systems, leading to lower operating costs. Imagine upgrading from an old energy-draining appliance to a modern, energy-efficient model that performs the same task with far less power, saving both money and resources. Real-time monitoring and control in microfluidic desalination are achieved by embedding sensors within microchannels to continuously track parameters such as flow rate, pressure, and ion concentration. This real-time data enables automated systems to make immediate adjustments to maintain optimal operating conditions, ensuring consistent water quality and efficient salt removal. For instance, a microfluidic desalination device equipped with sensors monitors salt concentration in real time and automatically adjusts flow rates to sustain optimal purification levels. It is like a smart thermostat that constantly reads your home's temperature and adjusts the heating system to keep the environment perfectly comfortable, regardless of external weather changes. Despite its promise, implementing microfluidic desalination technologies in real-world settings presents challenges, including scaling up from laboratory devices, ensuring material durability, and preventing fouling in harsh saline environments. Consistent performance over long periods and cost-effective manufacturing are critical for widespread adoption. Researchers are addressing these issues by developing advanced materials and protective coatings, as well as refining design protocols to ensure reliability and ease of use. For example, scientists are working on new polymer coatings that resist biofouling and corrosion, enabling microfluidic desalination devices to operate effectively in challenging marine environments. It is like designing a durable pair of hiking boots that can withstand rough terrain and harsh weather, ensuring they remain functional and comfortable for long journeys. The future of desalination using microfluidics holds promising potential for addressing global water scarcity. Ongoing research aims to refine these systems to enhance efficiency, reduce costs, and improve reliability through innovations in materials, sensor integration, and automated control. Future devices may even incorporate artificial intelligence for dynamic optimization and predictive maintenance, making them ideal for deployment in remote and underserved regions. For example, future desalination plants might integrate networks of microfluidic devices with AI-driven control systems to provide real-time water quality management for coastal cities facing water shortages. Imagine a futuristic water park where smart, interconnected devices work together seamlessly to filter and purify water, ensuring that every drop is as clean as possible, much like a well-coordinated symphony that creates harmonious music for an entire community.